This is a completely custom 3D printed ergonomic mouse. It was designed to perfectly fit my hand using 3D scanning. But this is more than just a simple case mod. It was designed from the ground up with an Arduino as its brain. And in this video, I'll show you how to build one. I have big hands, so I find that most mice are really a bit small for me. What's worse is that they keep on breaking. The last two that I bought only lasted about a year before something malfunctioned. On this one, it's the scroll wheel, and on this one, the left mouse button. And that's a problem, because they're not really that easy to take apart. But instead of simply buying another replacement, I decided to take matters into my own hands, quite literally. There's plenty of videos on YouTube of people making their own mice, but most of them simply take the circuits out of an existing product and print a new enclosure. That's perfectly fine, but I wanted to have more creative control, so I decided to start from scratch. Now, if you're going to go to the trouble of creating your own mouse, you might as well make one that fits your hand, and that's where photogrammetry comes in. Photogrammetry is a type of 3D scanning that doesn't require any special equipment. You can literally use any digital camera, even your phone. And there are free programs that you can use to generate the 3D model. The easiest way to do that was to just use some clay. So I headed down to my local hobby shop and bought a package of it. I grabbed a handful and worked it into a shape that felt comfortable. I don't really have any experience working with clay, so the first few attempts were really dry and hard to shape. But eventually I added a little bit of water and it got more pliable. I did actually do several of these before I got something that I was happy with. Fair warning, this can get pretty messy, as you can see. The next step was to start taking pictures. The photogrammetry process itself just consists of taking a bunch of pictures of the object from every angle that you can. The most important thing is to have consistency between the shots. Shoot in manual mode if possible. Keep the aperture, exposure, ISO, shutter speed, and everything else you can locked down so that all the images come out as similar as possible. Avoid depth of field or background blur as well as shadows. And when it comes to the program I'm using, it seems to work best if you leave the object stationary and move the camera rather than trying to put the object on a turntable. Something very important to note is how I placed the clay model on this piece of wood. That was done for two reasons. One, because I could move it without deforming it, and two, because I could get the exact measurement of the piece of wood and use it later for scaling the digital model. Meshroom is a free 3D program that turns all of these images into a high-resolution 3D model. How does it work? I have absolutely no idea, but it's pretty cool. Once the images are imported, you just save and hit start. About an hour or so later, depending on your system, you get a textured 3D model. With that done, it was time to fire up Blender. And I'm not really doing that much here, I'm just cleaning up the model a little bit. The first thing I did was to fix the model orientation and origin point. Usually they come out of Meshroom all flipped around at some random angle. Then I decimated it, because the polygon count is usually something insane like 6 or 7 million. After that, I switched over to the Sculpt tab and smoothed it down, because most of the scans seem to have this ugly orange peel type of surface on them. The point of all this was not to produce a finished model, but just to get something easier to work with. When I was satisfied with the model, I exported it as a .obj file and then imported that to Fusion 360. In Fusion, I used the known dimensions of the wood base as a template to make sure that everything was scaled properly. This is pretty important because, it needs to actually fit my hand. Now, as I mentioned earlier, the point of this model was not to be the exact shape of the finished product. I wanted something smooth, sleek, and clean, not a bumpy, wrinkled lump, even if that is technically the shape that was made by my hand. So what I did is to basically create a bunch of cross sections and draw polygons between them approximating the shape that I had scanned. This kept the overall fit, but also smoothed out the imperfections. I did make several different iterations of the clay model, and then I did also change several things in the 3D design as well. But in order to really test it out, you have to 3D print the model and hold it in your hand. So I did that. I ended up redoing the model and making a ton of revisions before I was completely satisfied. And so I had to print it out multiple times in order to make sure everything was good to go. Now, let's talk about the electronics. If you saw my Cyberdeck video, I mentioned using an Arduino Pro Micro to interface with the trackball, and that worked out pretty well. The important thing about the Pro Micro is that it has native HID USB support. This means that it can act as a mouse, keyboard, or gamepad on any computer. A normal Uno or Nano can't do that. Now, I already had a couple extra of these, so I decided to just use one as a starting point. But it wouldn't be much of a mouse without some kind of motion sensor. I found this module for sale on Tindy, a high-performance PMW3389 optical unit. This is basically a sensor chip attached to a breakout board that makes it easier to work with. It has extremely high sensitivity and accuracy, and the seller even linked to some example Arduino code. Perfect. Now originally, I was going to have a pretty standard approach to the buttons. 3D printed panels that could flex to press down on some switches. But at some point in the modeling process, I had a funny idea. What if I just use keyboard switches with standard keycaps? I mean, they're big enough to type on, and with a mouse that's a perfect fit for my hand, I could reach the right spot easily. The more I thought about it, the more I liked it. I even realized that I could put in a secondary button for each finger because they don't take up that much space. By simply recessing those, I could make sure that they didn't get hit during normal use. These low-profile switches are made by Kale, and are perfect for this design. They come in multiple colors, each of which represents a different typing feel. I bought both the red and white ones to compare, and ultimately settled on using the red for the main finger buttons and the white ones for the thumb. Now, the scroll wheel was a bigger challenge. First of all, they're not that easy to find for sale on their own. But eventually I found this part from KeyMouse. The first issue was that due to my decision to use the keyboard switches, I couldn't fit this between the left and right buttons. So I chose to relocate it to the side, where it could be controlled with my thumb. This may seem like a weird choice, but I really wanted to try it out. The bigger problem, though, was that I couldn't get the scroll wheel's rotary encoder to work properly. Most rotary encoders generate a set number of pulses per revolution. They have 3 pins, ground and 2 pulse pins. Depending on which pin triggers first, you can determine what direction it's rotating. But this one apparently didn't work like that, and so I couldn't figure out how to determine which direction it was rotating. The other issue was that I couldn't mount it very securely because its PCB had no mounting holes. So I started brainstorming alternative ideas. I had some other encoders lying around, so I came up with the idea of mounting one upside down and putting a knob near the base of the model. And luckily, I was able to get one of these working with an Arduino without any problems. This did raise another issue though, literally. I would have to move the circuit board up in order to accommodate the height of the encoder shaft. But the mouse sensor needed to be about 2 to 3 millimeters from the surface of whatever it's used on. To solve this, I decided to use a combination of female headers and a sort of backpack board that the sensor unit could mount to. The major upside was that everything could be modular and easily replaceable. However, before I finalized the design, I wanted to make sure that everything worked properly. So to test it, I created this monstrosity, which is ironically probably the least ergonomic mouse of all time. But it worked. Now, if I had any common sense, I would have stopped right there and built the final version. But instead, I decided to keep going and make my life a lot harder. I thought it would be really cool to do a wireless version of this mouse, but with the Arduino Pro Micro, that wasn't really an option. I did find a Bluetooth mouse library that works with ESP32s though. As for the microcontroller itself, the Feather S3. I chose this because it has an integrated battery connector and charging circuit, which would be necessary to power it during wireless operation. For the battery, I chose this 400 mAh model that fits perfectly between the rows of pins on Feather format boards. At this point, I made another test board, this time with the Feather S3 and an encoder to test if those parts would work together okay. I actually had a hard time getting the BLE mouse library to work with the PMW3389 code at first, but eventually, after banging my head against the keyboard enough times, I got something functional. During this time, I was also making alterations to the CAD model in order to try to fit all the components in a pretty confined space, and that was kind of a struggle. I decided that it was time to quit putting off the inevitable and finally learn PCB design. Now up till this point, I had only ever built circuits on a breadboard, or by soldering parts together using pieces of perf board, and designing PCBs seemed really intimidating. But it was becoming apparent that fitting all of the parts into that nice ergonomic shell I had sculpted was going to be no easy task. In order to get a cleaner, more compact footprint, I would need to create a custom PCB. So I downloaded KiCad and started watching tutorials. Luckily, it turned out to be easier than I thought. Since this is the first PCB that I've ever made, I decided to keep it simple and use through-hole components, since I'm kind of bad at soldering. And here's what I came up with. It's a simple dual-layer board that breaks out the Feather's pins and connects to 6 terminals for switches. It also connects the rotary encoder and a battery terminal. Plus it contains a NeoPixel-compatible LED connection point, but most importantly, it has the appropriate power and signal lines for the mouse sensor, which, as I mentioned, is actually mounted on a sub-board that connects like a sort of backpack to the main board. The mouse sensor has to be very close to the surface, so this arrangement provides the necessary clearance. Getting these manufactured was super easy, thanks to this video's sponsor, PCBWay. PCBWay offers a variety of services including not only PCB production and assembly, but also 3D printing in a variety of materials, sheet metal fabrication, injection molding, CNC machining, and more. All I had to do was export my files, upload them to their website, select options like board and silkscreen color, surface finish, and quantity, and I instantly got a quote to have everything manufactured and shipped straight to my door. I chose to use this black solder mask in order to match the Feather S3, and I think these came out really nice. I should mention here that I did also design an alternate version, this blue one. It's for a wired version of the mouse and uses an Arduino Pro Micro, just in case things didn't work out with the Feather, which, again, I'll get to in a moment. Anyway, both PCBs have the same footprint, component placement, and mounting points, so they're completely interchangeable with the rest of the parts. At this point, it was time to solder everything together. Now, as I mentioned earlier, I decided to go with through-hole components, even though they take up more space. I just find them easier to source and work with. Everything went together really well, and the mouse was working great, except for the buttons. Turns out I made a really simple mistake with the traces, but after fixing that and reordering the boards, everything was perfect. Once I had that finalized, it was time to fire up the trusty old 3D printer. I chose this really awesome color called Burnt Titanium, which is made by FlashForge. At first I thought this was one of those filaments where you get a gradient from top to bottom, but it's not. It's more like one of those custom metallic paint jobs you might see on a car. It kind of changes color as you look at it from different angles. The effect is subtle, but undeniably cool. Because of the hollow nature of the design, I had to print it with supports. Those were a little bit tough to remove, but with the help of some pliers, I got it done. All that was left to do was install the parts into the mouse body. The switches just pop right into these shallow cutouts and stay in place with a friction fit. No glue is required. I soldered some small flexible wires onto these to connect them to the main circuit board. This NeoPixel LED I added to the design fits into the hole near the thumb switches, and that I did secure with a drop of superglue. Over top of it, I placed a little plate printed from white PLA which diffuses the light quite nicely. For the encoder knob, I used this cool little anodized aluminum one. I did have to sand it a little bit to get the height right, and I also drilled out the hole so that it could slide all the way onto the encoder shaft. Alternatively, you could just print one from PLA. The board itself mounts to some threaded inserts which I installed into the underside of the printed mouse body. The sensor backpack module and Arduino can then be plugged into their respective spots. That just leaves the bottom cover. This was printed as a separate part which can be easily removed if the mouse ever needs to be worked on. You know, unlike commercially available ones. I chose to use white PLA for a little bit of contrast and to match the keycaps. On the bottom of this, I installed these self-adhesive mouse glides, which you can find on Amazon. And with that, the build was done. But before I go over the code, let me explain why the ESP32 version was such a pain. To make a long story short, I had two main problems. First, I had trouble even getting programs to save to the Feather S3 in the first place. I actually had to update the bootloader to even get it to work properly. And second, all of the example code was written specifically for Arduino, not ESP32. It assumed the use of a wired USB connection, but I needed it to work wirelessly, so I had to try to incorporate a Bluetooth library instead. I did get the wireless mouse working eventually, but it has some downsides. The latency is noticeably worse than the wired version, which is partly because I had to decrease the sensor polling frequency to prevent the pointer from moving inconsistently. It works well enough for everyday tasks, but I wouldn't recommend it for gaming. Now let's take a quick look at the code. I'll showcase the wired version's code, since it's a little bit less of a dumpster fire. I'll put a link to all the libraries I'm using in the video description. Basically, everything functions similar to how any project using an Arduino mouse library would, with some extra features. The PMW3389 library handles uploading the required firmware to the chip and returns sensor data as usable values that move the pointer around on the screen. There's a debounce function that eliminates signal noise and checks all the mouse buttons' state. It sends the corresponding click to the computer, whether it be left click, right click, middle mouse, or back. But there's actually 6 buttons total, so for the second, left, and right button, those actually send a keyboard command. These can be programmed to whatever you want, a single key or a macro. This is useful for both gaming and for applications where you just want a little bit of extra functionality. One cool feature is that you can change the sensitivity by clicking a combination of 2 buttons. This was already present in the library that I used, but I expanded on it by having it also cycle through color presets on the RGB NeoPixel LED so that you can easily see which mode that you're in. So how's the finished product? Well, it's far from flawless, and I do wish that the wireless version had been a bit more reliable. For now, I'll be sticking with the wired one. But overall, it's pretty awesome. The ergonomics are top notch. No surprise there, considering that it was tailor-made for my hand. The keys do feel different than standard mouse buttons, with a longer travel and a distinct sound. And then there's the thumb scroll wheel. It's unconventional, but surprisingly enjoyable to use. The sensitivity and accuracy are great, and I love being able to adjust them on the fly. I realize that this has been a standard feature on gaming mice for a while, but still. As far as the aesthetics, well, they say that beauty is in the eye of the beholder. Personally, I think it looks awesome, but I can also see how some people might find it ugly. I've been using this exclusively on my main PC for a couple weeks now, and I'm happy to say that there have been 0 issues. And if there ever are any, well, they'll be easy to fix. At the end of the day, I'm pretty happy with how it turned out. Anyway, I hope that you enjoyed this project. If you're interested in building something like this, I'm going to leave links in the description to the code, 3D files, and other documentation. Just remember that the model was obviously made to fit my hand, so it may not fit yours perfectly. But you could always create your own model and slap the electronics inside of it. If you enjoyed this video, go ahead and hit that subscribe button for more cool DIY projects. Thanks for watching!